Hello, this is Mr. Miller. Welcome to video 4F. I hope you're doing great today. In this video, we're going to start studying a topic called related rates, and this is the first of several videos on this topic. In the picture here, we see a balloon that is getting larger and larger. The radius is changing as a function of time. We see the first radius is the smallest, then it gets bigger and bigger. Because the radius is changing, the volume of the balloon is changing. And we want to know how these rates are related. For instance, if the radius is increasing at 3 inches per second, how fast would the volume be changing? So this is the kind of question we answer when we study related rates. Okay, in this problem we have a circle of radius 7 centimeters. And the radius is increasing at a rate of 2 centimeters per second. So the area would be getting larger as well. In fact, the problem is how fast is the area changing when the radius is 7 centimeters? Well, to start a problem like this, we have to start with a formula that relates the two quantities, radius and area. So we know for a circle that area is equal to pi times the radius squared. And everything is changing with respect to time here. Area is changing with respect to time, and so is the radius. So we're usually not going to write it this way, but just to see what's going on, let's write it like this. A of t, that means area is a function of t, equals pi times r of t squared. This is really what's going on. And when we take the derivative of r of t squared, we need the general power rule. All right, so let's do it. Let's find the derivative with respect to t. So the derivative of a would be dA dt, and it equals, we have 2 pi, it'd be r of t to the first power, so I'm just going to write r, times the derivative of the inside function, which is dr dt. Whoop, no t prime, just dr dt. Okay, so this is a formula for calculating the rate of change of the area. And it depends on two things. It depends on r, and it depends on dr dt. Okay, so here we have a graph of area equals pi r squared. So just to show you that the actual radius of the circle makes a difference, if the radius was 2, the y-coordinate of this point would be the area. And if it increased by 2 centimeters, the y-coordinate would only go up this much. So it'd go up from here to there. But if r is larger, like say 10, okay, the area of the circle would be the y-coordinate of that point. And if we let r change by 2, it would be way up here. The area would increase this much. So we see that the rate of the area is changing not only depends on the rate the radius is changing, but on the actual value of the radius itself. So when the circle's bigger, as the radius changes, the area changes much more quickly. But anyway, so we have this formula for dA dt. Now we can substitute what we know. dA dt equals 2 pi times the radius at this instant is 7, times dr dt. dr dt is 2 centimeters per second. And we have 2 times 7 times 2, that's 28. So we have 28 pi, and it would be centimeters squared per second, because it's units of area over units of time. All right, so when in this instant, when the radius is 7, if the radius is changing at 2 centimeters per second, the area is changing by 28 pi centimeters squared per second. All right, let's try to use this a couple times so we can get familiar with it. So this problem says the radius of a circle is 12 centimeters. So that's r. And suppose the radius is increasing at a rate of 3.5 centimeters per second. So that's dr dt. That's the rate of change of the radius. How fast is the area increasing? Well, we know the area formula is A equals pi r squared. And when we take a derivative with respect to t, dA dt equals 2 pi r dr dt, just like the last problem. And now we can just substitute information we have. dA dt equals 2 pi times the radius, which is 12, times dr dt, which is 3.5. So that'd be 7 times 12 is 84. That'd be 84 pi. And again, the unit centimeters squared per second. Okay, the area of a circle with radius 45 centimeters is increasing at this rate. How fast is the radius changing? This one's a little bit different. They give us dA dt. So 16 centimeters per second is how fast the area is changing. And we want to know it when the radius is 45. So it's the same formula here. So let me write down our formula. dA dt equals 2 pi r dr dt. And they just gave us different information. dA dt is 16. It's 2 pi times the radius, which is 45, times dr dt, which is what we're trying to find. So this time, we have to solve for dr dt. So we got to divide by this mess. So that'd be 16 over. 2 times 45 is 90, so we have 90 pi equals dr dt. And if you were concerned about the units, that would be centimeters per second. Okay, we have a real-world problem where these kind of growing circles occur naturally. If you throw a stone into water, you know that you get circular ripples, and these ripples spread out. And so their radius grows as a function of time, and so does their area. But here's a problem involving that. A stone is dropped into a still pond and makes circular ripples. If the radius of one of the ripples increases at 1.75 feet per second, how fast is the enclosed area changing when the radius is 10 feet? Well, here we go. So this is still using the same formula. We'll switch this up in the next problem. We have area equals pi r squared, or dA dt equals 2 pi r times dr dt. Okay, let's substitute what we know. 1.75 feet per second, that's dr dt, and the radius is 10. So we have 2 pi times 10 times 1.75. Okay, so 2 times 1.75 is 3.5 times 10 is 35. So we get 35 pi. And our units were feet and second. So this would be feet squared per second. Units of area per units of time. Okay, now if the area is changing at a rate of 26 feet per second, so they gave us the dA dt in this problem. How fast is the radius changing when the area is 130 square feet? Okay, so let's use the same formula. The dA dt is 26, it should be square feet per second. Kind of missed that in the problem. But anyway, 26 equals 2 pi times r. We don't know r. We know a, we don't know r. So I'm going to kind of leave a blank there. Times dr dt. Well, that's what we're trying to find. Okay, so I substituted what we knew into this formula here. Sometimes in related rates problems, as you're substituting into the formula, you come to something that you're going to have to solve for. For instance, we need to know r, but they gave us a. That's okay. If we know a, we can figure out r. A is pi r squared. So if a is 130, then we get 130 equals pi r squared. Or if we divide by pi, we get 130 over pi is r squared. Or r is the square root of 130 over pi. So we need the square root of 130 over pi here. What a mess, okay? But the only missing thing is dr dt, and we can solve for that now. So we can divide both sides by 2 pi, divide by this mess, and if you do it, you get dr dt equals 0.6433 feet per second. Okay, that was kind of tough. But hopefully you're familiar now. You can see that the most important thing is here is taking a formula like a equals pi r squared and taking its derivative. After that, it's just substituting values in algebra. So now here's a different kind of problem. This time we're going to deal with spheres and the volume of spheres. So a balloon has a spherical shape. Air is blown into it at a steady rate of 120 cubic inches per second. Suppose the radius is currently 9 inches. How fast is the radius increasing? So air is being blown into the balloon. It's getting larger and larger, and we want to know how quickly the radius is changing. All right, so we start with the formula. The formula for the volume of a sphere is given there. It's volume equals 4/3 pi r cubed. And here's the most important step, taking the derivative with respect to time. So the v dt, that's the derivative of v with respect to time, equals 4/3 pi. Now I'm going to take the derivative of r. This would be times 3r squared times the r dt. Remember, we got to use the general power rule. R is a function of time. Okay, so if I simplify a little bit, I get dv dt equals 4/3 times 3 is 4, so I get 4 pi r squared dr dt. Now let's fill in what we know. Air is flowing in at 120 cubic inches per second. That's the change in volume. So dv dt would be 120. Goes 4 pi. We know that the radius is currently 9 inches, so this is times 9 squared times dr dt. Now, 9 squared is 81. 81 times 4 is 324, so we get 120 equals 324 pi dr dt. And if we solve for dr dt, we get dr dt equals 120 over 324 pi. And the units this time would be inches per second. Okay, we could probably simplify that or find the decimal if you want, but I'm going to leave it like that. It's a nice exact answer. All right, what's next? This time we have an equilateral triangle that's growing. So it says the sides of an equilateral triangle are increasing at a rate of 1.5 centimeters per second. What is the rate of change of area when the sides are 13 centimeters long? Okay, well, start with the formula. Turns out for an equilateral triangle, a formula for the area is square root of 3 over 4 times the square of the side. Okay, so now we take a derivative. dA dt equals square root of 3 over 4. S is a function of t, so it's going to be 2s times ds dt. Or we get dA dt equals square root of 3 over 2. I just canceled the 4 and the 2 there. And this would be times s ds dt. Okay, so ds dt is 1.5 and s is 13. We're ready to go. The derivative of the area is equal to square root of 3 over 2 times s, which is 13, times ds dt, which is 1.5. Okay, and the units would be centimeters squared per second. Okay, again, we could multiply this out and get a decimal. I'm going to leave it like that. All right, we have two examples left. This one's going to be a little bit different. This time, we have a rectangle, and we're going to need the product rule when we take the derivative. So it says a rectangle has width 6 and length 8. Suppose the width and length are increasing at 2 centimeters per second and 4 centimeters per second respectively. Find the rate at which the area is changing. So again, we need a formula that relates the quantities in the problem. So area equals W times L. Everything is dependent on time. Width is changing with respect to time, so is length, so is area. So when we take the derivative, we need the product rule. So it'd be dw dt times L plus W times dl dt. But now we just have to plug everything in. So dA dt equals dw dt was 2 centimeters per second, and the length is 8 centimeters. W is 6, and the dt, the length is changing by 4. Okay, so we get 16 plus 24, which is 40. So we get 40, and it's units of area divided by time, centimeters squared per second. All right, in the figure above, suppose the width were increasing by 1 centimeter per second and the length decreasing by 1 centimeter per second. Would the area still be increasing? Well, I don't know. So let's use the formula again. dA dt equals dw dt is 1 centimeter per second, 1, times the length. The length is 8, plus W, the width is 6. Now, the length is decreasing 1 centimeters per second. So its derivative is negative 1 because it's decreasing. Okay, that's the first time this has happened in the problems we're doing, but something's decreasing, the derivative is negative. All right, so it'll be 8 minus 6, which is 2. So at this instant of time, the area would still be increasing by 2 centimeters squared per second. All right, we've made it to our last problem. So we've made it to a cylinder problem. So we see the radius of the cylinder is 4, and the height of the cylinder is 10. It says suppose the height is shrinking at a rate of 2 centimeters per second. So that's going to count as negative. While the radius is increasing at 1 centimeter per second. That's going to count as positive. Find the rate of change for the volume. Is it increasing or decreasing? Okay, so it's getting shorter but wider. So is the volume increasing or decreasing? That's a good question. So I'm going to start with the formula. Volume equals pi r squared h. Okay, we're going to need the product rule because we have a product of quantities here. So we have dV dt equals pi. And I'm going to work out what the derivative of this product is. It's the derivative of the first, 2r dr dt times the second plus the first times the derivative of the second function, dh dt. Okay, so we get dV dt equals 2 pi r dr dt plus pi r squared dh dt. All right, let's put in what we know. So this will be 2 pi, the radius is 4. The radius is increasing at 1 centimeter per second, so that'd be positive 1, plus pi times r squared, so that'd be 4 squared, dh dt. That's decreasing, so its derivative would be minus 2. So 4 times 1 times 2 is 8 pi. Minus 2 times 4 squared is negative 32. So minus 32 pi, which would be minus 24 pi, which is definitely negative. And that would be centimeters cubed per second. So since the derivative of volume is negative, we know that under these circumstances, the volume is shrinking. Okay, that was quite a workout, but hopefully you get a feel for the basics of related rates. So I have 3 problems for you, and they follow the examples very closely. First, a circle has radius 9 centimeters, and if radius is increasing at a rate of 2 centimeters per second, how fast is the area changing? Well, that's like the first bunch of examples we did, so I think you'll be okay in that. The second one's like the equilateral triangle example, except it's simpler. The area of a square is given by the formula A equals S squared, where S is the length of one of the sides. Okay, suppose the sides of the square are 10 centimeters long and are increasing at a rate of 3 centimeters per second. Find the rate at which the area is changing. Then finally, we have a problem like the rectangle problem. It has width 12 and length 20. Suppose the width is increasing at a rate of 4 centimeters per second, while the length is decreasing at a rate of 3 centimeters per second. Find the rate at which the area is changing, and determine if the area is getting larger or smaller. All right. Wow, that's a lot. Good luck.